Radiation. First we have Stephen Boltzmann law. It states that energy emitted from black body, denoted as EB, is directly proportional to absolute temperature to the power 4. EB is equal to sigma T to the power 4. Unit of EB is Weber per meter square, where sigma is Stephen Boltzmann constant, which is equal to 5.67 into 10 to the power minus 8. Black body is a perfect absorber, means its absorptivity, denoted as alpha, is equal to 1. Energy emitted for any body E is equal to epsilon into sigma into T to the power 4, where epsilon is our emissivity, which is energy for any body upon energy of black body. White body is perfect reflector, which means its reflectivity rho is equal to 1, and gray body is energy does not depend upon wavelength of radiation. So energy of black body is greater than energy of gray body is greater than energy of any body. According to Wein's displacement, wavelength is inversely proportional to temperature. So alpha 1 by alpha 2 would be equal to T2 by T1. Next, in this picture depiction, we can see on a body when irradiation is taking place, that is irradiation depicted by G is total radiation incident, then some part of it is reflected, some is absorbed and some is transmitted. The reflectivity, denoted as rho, is fraction reflected by total. Absorptivity, denoted as alpha, is fraction of incident ray absorbed, and transmittivity, denoted as Z, is fraction transmitted by total. In case of black body, when temperature is there, energy would be emitted. Irradiation which is taking place on a black body, the radiosity called as denoted as J, is total energy emitted when there is some temperature. Black body EB, which we have already studied, is equal to sigma T to the power 4, and for radiosity, denoted as J, is equal to rho G plus EB, where rho is part of incident radiation and EB is energy emitted from surface. And power absorbed per unit area is alpha G, and alpha plus rho plus C is equal to 1, alpha being absorptivity, rho being reflectivity, and Z being transmittivity is equal to 1. Then we have view factor. Now when we are taking two surfaces, then F12 is view factor, which is fraction of radiation reaching from 1 to 2. And there are two types of resistance taking place. One is the surface resistance, which acts on the surface, and then there is space resistance. So when there is an infinitely large plate, then F12, that is radiation taking place from reaching from one surface to 2, would be equal to 1, which means that all radiation from 1 would reach 2 when there is a large plate is used. So the surface resistance, the resistance due to the surface in case of radiation, would be 1 minus R epsilon by epsilon A, epsilon being emissivity, and space resistance would be 1 by F12 into area of 1. So according to summation law, our F11, that would be radiation view factor of radiation of plate 1 on itself, plus F12, F13, and for the number of plate would be 1, which means that total shape factor is equal to 1. Then according to reciprocity theorem, F12 into area of 1 is equal to F21 into area of 2, which means that radiation from falling from 1 to 2 into area of plate 1 is equal to radiation due to plate 2 on 1 into area of plate 2 would be equal. Then just like we had in conduction, using radiation network we are going to find our Q. When we have two plates having temperature 1 and temperature 2, it is denoted as T1 and T2, and the plate 1 is called EB1, energy of black body 1, EB2, energy of black body 2, just to depict two plates. Then SR1 is our surface resistance for plate 1, and SR2 surface resistance for plate 2, and SPR is our space resistance. So making a radiation network from this, because of the surface SR1, we have first resistance, then the space resistance is taking place, then we have resistance due to plate 2. So for the formula of surface resistance is 1 minus epsilon by epsilon into area. Then space resistance, the formula is 1 by F1 to A1. Then we have again our surface resistance. So we know that Q is equal to delta E by summation of resistances. So our final Q would be delta E is EB1 minus EB2, EB1 minus EB2 upon summation of all these resistances, which would give us Q. Then if there is infinitely long plate, then Q by A would be sigma into T1 to the power 4 minus T2 to the power 4 upon summation of resistances, and Q1 would be equal to epsilon 1 A1 sigma into T to the power 4 Q21, which it means that heat flux of surface 2 on 1 would be F12 area 1 of plate 1 into sigma and delta T to the power 4. This is basically heat flux on surface 1 due to surface 2. Then if a surface is enclosed in another large surface, like there are two bodies and surface 2 is inside surface 1, so F21 would be equal to 1. That is, radiation reaching from surface 2 to 1 would be 1, and F11, that is the view factor of surface 1 on itself, would be between 0 to 1 if the surfaces are concave surface, and in case it is a convex or flat surface, then the view factor, that is radiation on a body on itself, would be equal to 0. Then Q21 heat flux on 2 due to 1 surface 1 would be epsilon 1 area 1 in area of the first surface into sigma into T1 to the power 4 minus T2 to the power 4. Then we have shielding. Shielding is basically done to reduce the radiation rate, that is to reduce radiation flux or heat flux. Like between two plates, the one shield is inserted in this diagram, as you can see, and two large parallel plates and shield is inserted in between. So total heat with shield would be Q of shield 1 by n plus 1 into Q without shield. Like we have already studied view on based of view factor, that how to calculate Q without shield. So Q with shield would be 1 by n plus 1 into Q without shield, where n is our number of shields. So percentage of heat reduced, basically we are using shield to reduce the heat. So to calculate heat percentage reduced, we are going to subtract heat with shield from heat without shield upon heat without shield into 100. Heat Q without shield minus Q with shield upon Q without shield into 100 would give us percentage of heat reduced. And if there are n numbers of shield inserted between two plates, then we can use this formula of Q shield is equal to sigma 2 into T to the power 4 upon 1 plus epsilon 1 plus 1 plus epsilon 2, or to n numbers of our shield and sorry, this depicts our two surfaces, 1 plus epsilon 1 plus 1 plus epsilon 2 plus n number of shields, like whichever number of shields we insert between, into 1 plus epsilon of shield 1 plus epsilon of shield 2 plus 1 by n number of sheets, whatever number of, like if we have two surfaces and we are going to put 1 2 3 number of shield, es1 es2 es3, then it n would become 3, and we would have 1 by es1 plus 1 by es2 plus 1 by epsilon s3 in minus n plus 1. So with this we complete our radiation of heat transfer quick revision notes.